Hi everyone. I started the stream a little bit late because I had just sat down at my computer. I'm gonna let this run for a few more minutes, get myself some more water because I'm out, and we'll get started shortly. See you in a bit. I just really like this song, so I'm gonna let it play out here. So many good memories. There we go. We'll just wind that down. Alright. We'll get more Earthbound playing during the break here. Hi everybody, welcome back to Chem 161. This is the lab lecture for worksheet number 2. Which I don't have on the screen. Let me find it here. There it is. Oh, no, that's not right. Hold on. I don't know if that's going to show up. Oh, it did. Okay, cool. I only saw a very thin line on my screen here, so let me just expand this a little bit. Let's see. That's a little bit awkward. Hold on, let's do that. We'll get rid of that off the bottom of the screen there. I'm just downloading everybody's labs and trying to grade them. I've graded one class so far. That was 140. I'm going to grade the 161 ones next. Due to an issue, the third class, I will get to that eventually. It takes me time to grade your labs. Mostly because I don't really have any time during the week. I spend all day Tuesday lecturing and all day Wednesday lecturing. So I do some today, and then I do some on Thursday, and try and finish the rest on Friday. But I have other things that I'm also working on, too. So I will do my best to get the labs graded and returned to you as quick as I possibly can. And I apologize for any delays. It does take time, because I do go over them with a fine-tooth comb. For this week's lab worksheet, you're going to be working on content that we're actually going to be doing tomorrow in lecture and soon. So, worksheet number 2 uses the end of lab number 2, the end of chapter 2, and also a bit of stuff from chapter 6, which is actually the next chapter we're going to do. We do 1, 2, then 6. So, just a heads up. You can access that by going to the Modules tab, and clicking on Google Sheet number 2 for the online form. You know, I should probably get the lab open. That's the lab from the first period here. Let me see if I can find it. Those are labs I'm grading. This is close enough. 161 labs online. Worksheet 2. There we go. And then we'll just capture that as a PDF also. Boop. And I got to put that in front of the window so that you can see it. Let me do this, and we'll make this wider. Okay, so lab worksheet number 2 is going to do a lot of calculations with moles and titration. These are techniques that we covered at the very end of 140, and we're going to review them here. You're not really going to use these calculations terribly much in this class, except for, like, just some basic stuff in the end of Chapter 2 and Chapter 6, like we just said. But these techniques are going to be very important for future labs that you do in this class, as well as calculations that you will do in 162. You spend all of 162 doing this stuff. So it's important to understand how to do it, and then keep that on the back burner so that when you go to 162 next quarter, you have it right at your fingertips so that you can do it. So the first part's going to involve a solid hydrate. A hydrate is an ionic compound that contains water in it. Now, the water is sort of just loosely bound. What that means is that the water molecules form interactions with the compound. Typically, that's the metal ion that is involved. So, like in calcium chloride, if calcium chloride was a hydrate, the water would be bound to the calcium as well as the chlorides. And they would incorporate into the crystal structure in a repeating lattice that we'll talk more about in Chapter 4. The important concepts to understand here are the mole concept, which we're going to talk about tomorrow. But you probably remember what a mole is from Chem 140 or high school chem. A mole is 6.022 times 10 to the 23 things. And what we can do is we can figure out how many moles of each element are in the substance by doing an analysis. So for this lab, we're going to do several analyses of solid compounds. The first one we're going to do is copper chloride. I give you a video, which you can watch. You're going to have to watch the video and obtain numbers from that. Here are some timestamps in that video to watch it. It's 10 minutes long. You don't really need to watch the whole 10 minutes. Just kind of flip through to get an idea of what they're doing, and then find the numbers that are relevant, because you're going to be using those. Let's hide this really quickly, and we'll go to here. And I'm going to draw out the general procedure. Let's zoom this. Oops, I hit something else here. Where are all my shapes? Why is this? Hold on. Let me try and get that back. There they are. Okay. I didn't have any commands on my screen here, so that was kind of weird. Okay. So here's the general gist of what we're going to do. So you're going to have some sort of solid, and I'm just going to draw the solid like this. So this is my solid, and we're going to say that this is, we'll use copper chloride for the, or are we doing copper chloride or copper sulfate? Let me look at the lab real quick. One class does one class does the other. I think you guys get copper chloride. Yeah, you get copper chloride, okay. So I'm going to go CuX, because we don't know how many coppers there are per unit. Cly, because we don't know how many chlorine there are. And then I have some amount Z of water. So X, Y, and Z are coefficients. So, for example, maybe the formula is Cu to Cl3 dot 4 H2O. And so what that would be is that for every 2 copper and 3 chlorine there are also 4 water. Now, those aren't the numbers. I'm just making those numbers up. You're going to calculate different numbers based on the data. So what we're going to do is we're going to put this into a crucible. A crucible is just this little tiny container. We're going to fill it with our stuff. There it is. You can see it inside. And then what we're going to do is we're going to heat it. So if I heat it with a blue flame from a Bunsen burner, and my Bunsen burner and my crucible are going to be mysteriously floating. There's the gas line, whatever. There's some apparatus that you would hook this up to. For simplicity, we're going to do this. We're going to heat this over the crucible. Now, when you heat this, its temperature increases, and anything that is loosely bound will then evaporate out. And so the loosely bound substance in our hydrate is the water. So H2O will be boiled off. And then when we're done, inside the crucible will be something that's a different color. I had to find where in my palette I have that color. There, that's good. Okay. So then when we get the crucible, so after heating, our crucible, oh, I'm going to sneeze. Hold on. Let me do this. I'm going to hit mute real quick. I think I hit mute in time. I apologize for that. All right. After heating, our stuff will be a different color because hydrates tend to have different colors in them, whether there's water in it or not. So now inside of this is just this stuff. The water is gone. How do we figure out how much water is in there? Well, we could say, if I weigh the mass of the crucible and the mass of the copper and the chlorine and the water, that's the blue stuff. So that'll be this, and we'll just say that it has some mass. This right here, that's not going to be a good line. Hold on. We'll go like this. This will be the mass of the crucible, because that's still there, and the copper, and the chlorine. But the water is gone. So what we'll do is we'll just subtract these two. So minus, And since these are both present in each of these, when I subtract, they'll get canceled out. They'll be subtracted away. And so that the mass that I get down here will just be the mass of H2O. So by heating off all of the water, we can then measure the mass before and after this heating has occurred, and we'll know how much water was in there. Okay, that's cool. So we got the water part figured out. The next thing that we're going to do is we're going to take the copper chloride. So here's our copper. We'll go like this. So this is step 2. This is step 1. Step 2, we're going to take our copper chloride. Ooh, that's terrible. Hold on. There it is. It's in my crucible still. And then what I'm going to do is I'm going to dump this in a container. With water. And a little HCl. And an aluminum wire. And so we'll go like this. So this will be my aluminum wire. When you do this, the copper chloride will dissolve into the solution. And what ends up happening is this brown stuff will change color. It'll change back to blue. And the reason that the brown turns back to blue is because we have reintroduced the water to it. I've dunked it in a solution of water. So this is an H2O and HCl solution. The HCl is just to promote the reaction. And we'll put and the copper chloride, which is now in here. What the aluminum wire does is the aluminum does a reaction. And so the aluminum will react with the copper, which is an ion, because it's an ionic compound. And what ends up happening is that the aluminum becomes an ion, and we get the copper metal. And this X and this X are not necessarily the same. They probably should be, and then we would have to balance the equation for that. But that is shown in the lab. You don't have to really worry about that equation. I'm just writing it because this is what we care about. Because when this is done, what our container will look like, and what I should really do with the aluminum wire is kind of do this with it. So there's my aluminum wire. We're going to have copper metal plate out onto this wire. That's not the brown color I want. There we go. And so I'm going to get all this copper. So this will be copper metal. And the chlorine just stays dissolved. So now what we can do is we take the wire out and just have copper metal. So, oops, that's not the right button. So then we'll have the copper metal, which is now isolated. And since it's isolated, you can weigh it. And once you've weighed it, you know the mass of the copper. So this one's done. And then finally, once we know the mass of the copper, the mass of the chlorine must just be, okay. I know what the mass of the copper chloride was because I weighed it up here, right? And I know what the mass of the crucible is because we weigh it before we do the experiment. So we can subtract that out to just get this mass. I'll just subtract the mass of the copper that we got right here. And when I do that, what must be left is the mass of chlorine. So now we know that too. So in the experiment, we're only going to isolate the water by heating it off, and then the copper by precipitating it using this aluminum. The chlorine, we don't ever calculate directly. We do it indirectly, using the other numbers that we get from the lab. Now, for the other ionic compound hydrates that you have, you do the exact same principle. You heat it up to get rid of the water, you precipitate out the metal somehow, you calculate the mass of the water and the metal, and the remainder must be the non-metal. Okay? So that's going to be the premise for this first part of the experiment that you're going to do in the procedure. Okay? So I ask you some questions about the procedure, and then I ask you to do this sample experiment with copper and oxygen, and then suppose that we only have copper and oxygen in the air. We don't have any water. And then when I do the analysis and I isolate copper, I get this much copper. So you could do the same thing to figure out the masses of what was in there. Now, remember that formulas don't really care about masses. Formulas care about moles. So all of these masses that we calculated here in this experiment, you're then going to eventually turn all of your masses into moles. So once you have the masses, you'll turn them into moles. And from there, you can make the formula. We're going to show how to do that tomorrow when we talk about moles. But the gist is, if you remember that we make like a pseudo formula, so if I had like 0.3 moles of copper and then 0.6 moles of chlorine, then what I would do is divide both by the smaller number, and then I would say, okay, this is what I get. For example, if I instead had maybe this number, then I divide by both by that, and I would end up here. All right, that's the gist of it. And for the most part, this should all sound familiar to you. All right. I'm going to give you, in the lab, some experimental data. And so I have done this experiment for you, so what you're going to have to do is determine the calculations here. Okay, I know what the crucible weighs by itself. Okay, I know what it weighs after I put the stuff in there, and then I heated it, and that's what it weighs now. So from that, you could figure out how much water was there, because the water must be, okay, here it was before with water, here it was after I heated it. So I'm going to subtract these two and put the answer there. You can then turn that mass into moles, and then you can use the mass of copper recovered and continue from there. And then I have you do the formula of a hydrate, and I guess that's everything. Yeah, okay. I guess I don't give you multiple of these to do, because that could have been 140. All these labs are similar. They get mixed in my head. When you get your formula, you should get whole numbers for it, because I've tinkered with the data to give you something very close to a whole number. Okay? Do each trial separately. Don't do any averaging. Okay? Treat these as individual separate trials, and be mindful of sig figs, okay? Because you're going to be doing subtraction, you're also going to be doing division and multiplication, and each of these has their own correct sig figs based on the numbers before it, okay? So be mindful as you do the calculations that when you put a number here in this box, you put the right number of sig figs based on these two numbers here. All right, and then you answer the questions after. Any questions about part A of the experiment? I'm going to hide this real quick, and then we'll just go back over here. We'll just slowly pan over this. You can pause the video if you need to copy it down. All right. I'll give you a minute if you have to type in any questions. I'm just going to drink more water. Spend a few minutes every hour doing nothing but drinking water. That's the key to hydration. What is wrong with you people? Just drink more water. Myself included in that. I don't drink enough water. Refreshing. All right, let's go to the next part of the experiment. So I'm going to clear all of this away. Boop, it's gone. Gone forever, except not because it's streamed. You can always go back if you need it. Let's talk about part 2. Part 2, or part B, I should say. Part B is a titration. And so what we're going to do, I already have a picture of it here. We're going to titrate by adding a strong acid and a strong base. You don't really have to worry about what acids and bases are yet. We'll talk about that in more detail in 163. Suffice it to say, these are very simple equations, and this is the equation that you're going to study. Oops, excuse me. We're going to react HCl with sodium hydroxide to make sodium chloride and water. The way that we're going to do this is we're going to have one of these be a known concentration, and then the other one will be unknown. I believe that the sodium hydroxide is the known amount. I show you how to do some basic molarity calculations, and then I have a video for you to watch the titration. I just want to see which one. Yeah, okay. So we have a known molarity of sodium hydroxide. So let's go to this and draw what's happening. Okay. I got to get a different color out here because this brown is just bad. All right. So we have our burette. That's the worst. That's a burette from the bargain bin store. There's our burette. That's a little better. So this is our burette. And inside the burette is sodium hydroxide. And it has a concentration of 0.2000 moles per liter. Now, if you're looking at that going, hey, we haven't studied molarity yet, that's fine. It's Unit 6. We'll come up to that very shortly. We're going to do a little bit of a review for that today, too. We're going to titrate that into a flask. Let's see if I can do better there. That's a little better. You can tell I have practiced doing art because I have my hand on the undo button here. And inside our flask here is going to be HCl, and its concentration is unknown. Our job is to titrate and determine how much is in here. So what we're going to do is we're going to open this by turning it, and then this will go into the container, and the reaction will proceed until it turns pink. Okay? When it's pink, it's done. It has reached the endpoint. Okay? Why does it turn pink? The reason for this is because we've added an indicator in here. So the endpoint comes from... Oh, darn it. The endpoint comes from the indicator. You might recall that in acid-base reaction, all the components are colorless, and the result is sodium chloride and water, which are also colorless. So what we do is we add a pink indicator to determine, oh, there is excess base in here. So what that means is that when the reaction is done, this will have decreased, and we will have a volume of NaOH that was added. Here's the reaction that we're doing. And once I add sufficient NaOH to completely react with HCl, all of this is gone. If I add extra NaOH, what it does is it reacts with the indicator and produces pink, which means that the titration is done. Okay, so the reaction is incomplete while the flask is clear. The instant that the reaction is done, it would still be clear. But if you go over by even half a drop or 1 drop or a tiny little bit, then you start to see pink, and the reaction is finished. So what we do for our titration technique is that we're going to add sodium hydroxide until you see the faintest pink up here. And then once the faint pink has appeared, you stop the titration. And then we have the following quantities. We know how much volume of NaOH we added because we can measure where we started. This would be V initial. This would be V final. I know the concentration of sodium hydroxide because I told it to. And I don't know the concentration of the HCl, but I do know the volume that we use of it. Because I had to put some amount of HCl in there, right? With those three things, we can calculate the concentration. And here's how we do that. The molarity of anything is how many moles of that something you have in there divided by its volume. And so I can rearrange this equation to say the molarity times the volume would be equal to moles of X that are in there. Or in other words, whatever the molarity of the substance we're looking at times the volume that we used of it is moles that we used. Okay, so we could say molarity of sodium hydroxide times the volume of sodium hydroxide used would be the number of moles of sodium hydroxide that are in the container, or that were in the burette that we use. So that would be, this right here would represent this chunk right here that we used. Then what we can do is we can say, okay, well, if I go to the balanced equation up here, which is very simple, for every 1 HCl I react, I also react 1 sodium hydroxide. So what that means is that for every mole of sodium hydroxide that's reacted, I also react a mole of HCl. So by knowing the number of moles of NaOH that were in the burette, we also know the number of moles of HCl that are in the beaker, because we react them 1 for 1, and if we stop at the end point, we didn't put too much NaOH in there, we put just enough. And then finally, if we remember what this relationship is right here, that molarity is just the moles of stuff divided by its volume, you could then divide by the volume of the HCl that you put into the container to get the molarity of HCl. So that's the gist of the experiment. Your goal is to start with a known sodium hydroxide concentration and volume, and from that, titrate it with a known amount of HCl, and calculate the molarity of it. So you know this number, you know this number, and you know this number, and from these two together, you can get to this. Oops, that's not where I want to go. You can get to here, which then you can get to here. All right. So this is all review from 140. So let's go back to the PDF. You're going to get a bunch of data. Here's my start point on the burette. Here's my end point, so you know what volume was used. These are all in milliliters, so be mindful of that. Remember that molarity needs liters, so you're going to have to do some conversions. Once you know the number of milliliters you used, you know the number of moles that you used, because I told you its concentration up here. Once you know the number of moles of sodium hydroxide, you know the number of moles of HCl. I use 25 milliliters. You can get the molarity and then calculate an average. Should be really straightforward, as long as you don't get lost in the numbers. Just looking at this without the picture is kind of rough. So, oops, that's the wrong thing. There we go. Refer back to the video, and also refer back to this lecture if you need to. The video being the video that's linked in here. Where is it? There it is, right there. And then I have some more post-lab questions that you want to answer. All right, so now that we're done with that, we can go back to this. Here's your worksheet. Exactly the same process as last week. It's just that you notice that there are even more tabs this time, but the tabs are in general shorter. I still don't have point values on this, so don't worry about that for now. I will fix that. It's written in my master key. But again, any box that you see like this, you're going to type out a description. Keep it within the bounds of the description. In fact, I noticed that these are not formatted. There we go. So we'll do that. Here are the tables from the lab worksheet. You're going to put the numbers into the tables that you calculate. An important thing to note about these tables is that they are not formatted for numbers. So what that means is that if a cell is formatted as a number, and I type in 0.500, what Google tries to do is it chops out all the zeros. It thinks that they're worthless. Over here, I have formatted these as text so that you can just enter the numbers in there and they will stay there. But what that means is that you cannot use a formula command because the Google might not know what that is, okay? So be careful. It looked like it was working there, actually. Yeah, it did work. Okay. I would avoid using formula commands in general and do all this work on paper, but if you want to use formula commands and it works, then that's fine. All right, so that's part A, and then here's your questions again. Let me format these so that they all go to the top. So I want to repeat. Okay. We'll just keep doing that. Here's another table. There's the last part. And I believe that's it. Okay, so lab number 2 is pretty straightforward if you remember your 140. If not, we're going to be reviewing this content in lecture this week, so keep an eye out for that. If there's any questions about part B or about the lab worksheet in general, everybody should be able to access it. What I'm going to do now is I'm going to go over here. We're going to make the assignment available so that you can turn it in. Lab worksheet 2. We're going to edit this. You can upload as many as you want. Assign to everybody. Let's do next Tuesday, and then the hard deadline will be the next day. There you go. So it is now open. You should be able to see it. I think you can actually see the other 3 that are there. In fact, what I should probably do, we should just get rid of these. There you go. So now you can only see the ones that are due. You don't have to look at these and go, what do we have to do for these? Because they're not up yet. Or they're not due yet. Okay, there you go. That's it. That's all I got. Are there any questions? Let me know. I should probably mute while I'm drinking water here. All right. So we're not done yet. Technically, this is a Q&A session. So now what I do is I go back over to here. I'm going to put the timer up. And I'll just let the timer run for 10 minutes. And if you have any questions about anything in the class, so like quiz number 1 is closed. You can ask me questions about quiz number 1 now. Or about content from chapters 1 or 2 that you want to go over again. Everyone did great on the quiz, by the way. Like, the average was very high, which I expect because, surprise, it's all that shit from 140 again, right? And you all did really well. So I have very high confidence that everything we're doing today is going to be fine. But if you do have any other questions, let me know in the chat. I'm going to start the timer, and I'll come back in 10 minutes, and we'll go over any questions that you might have. So we'll see you in a bit for that. Let's find a good song here. There we go. Alright, I'm back. Well, I was always here, so... So let me go into here. Let me close that. So what I'll do, let me look at the quiz here. I have to find the specific question, which always takes me a second, so it's probably one of those. Okay. Mostly because when I give you a quiz, this is what I see. I can show you this part. So this is what it looks like when I make a quiz, just in case you were curious. And this keeps going over here. And so all my questions are pooled. So like I have a question from this, but when I go and click on it, that's all I get. I don't get to see the question anymore because it's in a pool. So I had to go to find all the pools, and look how many freaking pools I have. This is page 1 of 7. Like it's a miserable mess how Canvas does this, and unfortunately, this is what I get to work with. So I had to find the right pool. And apparently, Chem 161 starts on page 5. I tried 4 and 6, and it wasn't there. It's terrible. I hate Canvas. Like, if I was writing you a quiz, I'd give you a piece of paper with my questions on it, because my pool is my brain. And it takes me 20 minutes to write a quiz. This takes me 4 hours. So let me see if these are the questions that we want. There's nothing about lettuce in here. Okay. Maybe it's in here. There's a balloon. Here we go, yeah. Okay, so the intent was that for the lettuce question, excuse me. So one of those statements is a specific question. So the specific there is that we're specifying that lettuce does not give any, you don't get any energy or weight from it. So that would be a fact because it's specific to lettuce. So somebody did this experiment, they ate lettuce and did not get any weight. Then the next statement that I have is, for humans, the energy content of leafy green vegetables is nearly 0. So there I said leafy green vegetables. So that includes lettuce. So what that is implying there is that not only have we tested lettuce, but we've also tested things like spinach, cabbage. I'm trying to sit here and think of leafy green vegetables now. I wanted to say broccoli, but broccoli is not exactly leafy. But you get the idea. So there are multiple things that fall into that category. And so that's not just a fact, that is a bunch of facts conglomerated together to explain what's going on, but not the why that is happening. And so that would be a scientific law. And then the last statement I had was, plants composed of primarily of cellulose do not provide caloric nutritional value because people lack the enzyme to break it down into glucose. So that right there should tell you a why. Oh, this is why we don't get energy from these things. We don't have the enzyme that breaks the beta glycidic linkage in cellulose. Sorry, I'm doing biochem. We don't have the correct enzyme to break down cellulose. So we can't get energy from it because it just stays cellulose, and so it passes through your body as fiber. That explanation there tells you, oh, okay, I understand why we can't get that due to the word because, da-da-da-da-da-da. And so that's your theory. So to sum up from what's in the chat, a fact is a very specific observation from one experiment. A law is a collection of a bunch of observations. Yeah, kale. There you go. Thank you. I used to eat tons of kale. I haven't eaten kale forever, actually. A law is a collection of experiments, so a bunch of facts put together. And then the theory takes that law and explains it in more detail by doing a bunch of experiments to try and understand that. So that's the difference between those three. Oops, I almost changed the quiz. I do not want to do that. And then the other question, where the heck is it? There it is. Can I go over the gold question? Which question is the gold question? Is it the gold coins question? Do I have that in here? There it is. Okay, it is quiz 1. Oh, I can't copy and paste this because it will just print out. So what my problems look like is I assign a variable, and so it just says, Monty finds a gold pile of exactly gold coins. That's not going to help anybody. But yeah, I can show that problem. So let me go like this. So the information that I have in that problem, and this should be somewhat familiar to you. Let me just throw this on this monitor over here while I'm working. I can't see the chat for a second because I got to copy stuff down. All right, so I know that I have, I'm going to just pick a number of coins. I'm going to say that I have exactly 25,000 coins. And I know that a single coin weighs 0.2 pounds. And I know that Monty weighs, I don't know, we'll make him 155 kilograms. Sure, that sounds good. I have no idea how many sig figs were intended for this based on the numbers, because I can't see the numbers I'm entering in. I'm going to guess 3, and I'm going to write that that is exact. Okay. All right, I can see the chat again. All right, so to do this, I want to figure out how many Monties there are in this pile of coins. So what I would do is first I got to figure out how much the coins weigh. So one coin is 0.02 pounds. And then I have pounds and kilograms here, so I'm going to need to turn this into kilograms. And let's see here. 1 kilogram is this many pounds. And then once I know how many kilograms I have, I can figure out how many Monties that is. So 1 Monty is 155 kilograms. So if these were the numbers that you had, times 0.02 divided by 2.204 times 155. So when I do this, the number I get, this was my result, and then the units of that would be just Monties. So he found enough coins to weigh 1.46 times his weight. So that was the intent of that problem, was for you to do a calculation like that. Cool. Did I give you both that one and then the Donovan problem? I think I have both of those in here. Actually, I don't know. Let me scroll down here. Yeah, you got both of those problems in this class. Last quarter, I reused these questions and I just changed them around a little bit. Oh, if I had scrolled down, I could see an actual copy of this. Okay. But yeah, okay. Cool. Any other questions? Let me know. All right, last call for questions. Got anything, let me know. Otherwise, I gotta go figure out what I'm gonna do for dinner. It won't involve kale. I don't have any. Which is too bad, because I like kale. Actually, I think I know what I will eat for dinner. I have had kale chips, and I wasn't really impressed, actually. I liked the kale better as kale, to be honest. I think it was because they're too thin. Like, kale is pretty thick on its own, but when you dehydrate it, it gets, like, really, really, really thin. And I just wasn't interested in it. Like, it's nice and crispy and all. What I used to do when I would get kale is I would chop up the kale and throw it in a bowl, and then I would cook chicken and mushrooms and just pour it over the kale, and then have a salad. And I would just do that all the time because I love salads. I love all food, really, except seafood. I'm not a big fan. Um, is bronze statues a mixture? Yes. So a mix. All alloys are mixtures. So bronze is a mixture of tin and copper. And if you aren't sure if something is a mix or like an alloy or something, you can do two things. One, look for it on the periodic table. If it's not there, it's not an element, and therefore is most likely a mixture. And then two, you can always just type into Google, what is bronze made of? And they'll tell you. So common alloys are steel, bronze, brass. Electrum is silver and gold. Pewter is I believe, is a mixture of. What is pewter? Shit, I can't think of that. Baffled at your own response. That would probably be something that would be better for me to answer in private so that you could tell me your answer, because I can't disclose your answer on the air. I can look at everybody's individual responses. Unless you meant along the lines of, I don't know why I did that. That seems silly. That is a feeling that a lot of students have when taking quizzes, because you make mistakes and then you learn from them. Okay, cool. Yeah. If you look at your response and you're like, that was dumb, here's the answer, I know why it's the answer. Congratulations, you have learned. That's called learning. That's a good thing. Excuse me. Part of learning is making mistakes. I made so many mistakes in college. Trust me. I went to UC Irvine, and I remember getting my exam back and being like, wow, I only got 62%, which turns out that that's like a B. It sure didn't feel like a B. But I felt dumb for like all the mistakes that I did. And I was the kind of student that would get really depressed because it was like, I know all of this. Why am I making these mistakes? Everything is the worst. Lead and silver, that sounds right to me, yeah. Pewter does have lead in it because it's super heavy. But if there's anything I can encourage you from looking over your results is don't get depressed about it. There are so many better things to get depressed about right now, like COVID. Like, yeah, we can all be miserable about that. That's totally justified. But like 1 or 2 points on a 10-point quiz, or however many points your quizzes are worth. I think yours are worth 25 now. Like 2 or 3 points on a 25-point quiz, don't sweat it. At the end of the quarter, if you are close to an A, I give you an A anyway. I round all your scores up slightly at the end. So don't worry about it. Don't count on that, obviously. Like, if you're missing 400 points, I'm not going to go, well, here's 400 points in a 500-point class. But if you're missing, like, 7, yeah, I'll just give it to you. All right. Other questions? Pewter alloy. No, I'm just curious here. It says mostly tin, antimony, copper, bismuth, and sometimes silver. Okay, maybe it isn't lead. I was thinking tin, but I honestly didn't know. Oh, down here it says less commonly today lead, but that's what's mixed into it. So traditionally 85 to 95% tin is what I'm seeing. Does the vaccine work? There is data out there that suggests it's 90 to 95% effective. I personally have not gotten vaccinated yet because my position in the queue is like May. I'm late. I get to go after everybody in phase 1. But the second that it's available, I will get it. Absolutely, hands down. I think everybody should get vaccinated unless you have a great reason not to. And by great, I don't mean, oh, I am afraid of needles or, oh, I don't believe in vaccines. Those are bullshit answers. A great reason to not get the vaccine would be doing so might be deadly. So, like, I know some people who couldn't get certain vaccines because it, like, deteriorated their muscles because they had, like, an adverse reaction to something in the vaccine. Um, so, like, an allergy, that's a very valid reason not to get a vaccine. But any other reason, they're like, oh, I don't like it, or oh, I don't trust it. Like, that screams to me like who are you listening to when 99% of scientists who have been working on this stuff for years say this has been shown to be effective, and then you hear random one or two voices on the internet from Twitter or whatever say vaccines are a scam. I mean, just look at the numbers of people saying what is going on versus the other people shouting in an echo chamber. And to me, the science speaks for itself. There's been a lot of research. They've been doing tests and stuff like this since March of last year, or February or earlier. And the trials have gone underway. Yeah, it's going quickly because it's an emergency. But the science is still the science. Am I teaching biochem? No, I don't have a biology background. I know just enough biochem to get by. But I don't teach anything in the bio department. I'm more of a physics chemist, so I could tell you like all of the physics formulas and stuff. We're going to do a lot of that in chapter 3 this quarter. We're going to talk a lot about the physics nitty-gritty with Coulomb's law and stuff like that, but I don't really do much of the bio stuff. I took one bio class in college, and I slept through most of it because it was so boring. Is that Ricky? Some of the instructors, I only know their first name. I mean, I can look them up in the directory. Yeah, that's Ricky. Ricky's a good guy. He's very enthusiastic. I don't know that many people in biology very well, actually. I know of them because I see them at like department meeting. I really only know the chemistry department well, and also, interestingly enough, art, because chemistry, chemistry, physics, geology, and then art, because it's all in engineering. It's all in the same building. Biology is actually in a different building, along with computer science. We've organized things weird at Everett Community College, but it's also like kind of great in a way because I walk out of my office and go upstairs, and then it's just all art, and I get to see all the art that people are doing. And so like, there's all the charcoal drawings and all the paintings and all the pictures that people do where they sit in the hallway for hours on end drawing exactly what they see from perspective. And now I'm getting super nostalgic about going back to work because I really just want to be in the classroom again. Oh, now I have a sad. Any other questions? I'm gonna go eat tacos and cry. I probably won't cry. I will definitely eat tacos though because I have the stuff for that. I have an onion in the fridge that I can use the rest of. We'll just go back to here. All right. Oh no, it's the music. It's playing. I guess it's time to go. All right. Thanks, everybody. I will see you tomorrow for lecture. We're going to finish chapter 2 and go to chapter 6. Have a good night.